it's with great pleasure I'm now introducing our next speaker. So this is work from Beijing University, and it's on deep generative ranking for personalized recommendation. Our speaker is Huafeng.
Okay, thank you. It's my great honor to be here to introduce our latest work on deep generative ranking for personalized recommendation. And I'm from Beijing University, and this work is a joint work with Generative, Epinions and Generative. I'm sorry, maybe the figure do not chemistry. Because I have a figure here. No, it's not like I'm just switch your finger. Keep on going. Okay, I think it's okay. Yeah, it's okay. Okay, let's go. So, the recommended system focuses on identifying user item preference pattern. So, the most famous model is a latent factor model, right? For example, a matrix factorization is to focus on to learn the user item embeddings or user item factors to predict the unknown ratings, right? And recently, deep learning is also employed to build a recommendation model. For example, here is a framework of the NCF. It's a really popular model, and we know that we can call this model generalized matrix factorization because this model introduces a nonlinear feature into the traditional latent factor model. But this model has two issues. The first one is the high bias between the predicted data distribution and the true data distribution. The second one is it do not suit for the sparse data set because we use the deep learning or deep neural network. And so the deep generative recognition model is combined with this latent factor model and the advantage of the neural network, which is employing nonlinear probability latent variable models powered by neural networks. But there still have two issues. The first one is it do not have an explicit learning to recognize if we focus on item recommendation. And the second one is it do not suit for sparse data. So in this paper, we focus on item recommendation and we create a deep generative ranking model by combining two parts. The first one is called pointwise feedback data generation. The second one is called pairwise ranking-based creation. So this model can exploit nonlinear feature and also take advantage of the data factor model. So let's introduce the first part. The first part is pointwise feedback data generation, and in this part we propose a Beta-Bernoulli nonlinear latent factor model. Why we call it Beta-Bernoulli nonlinear latent factor model? Because we introduce a ranking score vector pi I, and we think the pi I is generated from a beta distribution. And also, the feedback data set is generated from a Bernoulli distribution parameterized by a ranking score pi I. So all this model is called Beta-Bernoulli model, and this is likelihood. And we set the auto-encoder framework to measure the distance between the true dataset, true data distribution, and the generative distribution, which enable us to sufficiently to reduce the construction error. And the reason why we use Beta-Bernoulli distribution, beta distribution here, because we think it's more suited for sparse dataset. Because you know a beta distribution control the generative ranking score, because a beta distribution have two parameters. The first one is alpha, and the second one is the beta. If we control the alpha and the beta greater than 1, and also alpha is greater than beta, we can produce a small high I, and also we can generate a more sparse xi. So we call this model is more suited for sparse data. And the second part is a pairwise ranking list creation. So in this part, we propose a deep Bayesian personalized ranking, and maybe motivated by the traditional Bayesian personalized ranking. But we create a pairwise triple dataset according to users' positive, unobserved, and negative dataset. And also we introduce probability based on the user's ranking score and sigmoid function to measure the user's ranking score. And also the likelihood is looked like this. And we combine these two parts like this, combine the Beta-Bernoulli generative model and the deep Bayesian personalized ranking model, and we obtain a final model here. And also we give some theoretical analysis based on the generalization, which we defined on the feedback data set generalization process, and we measure the true dataset and the generative dataset and give the theoretical analysis like this. Okay, we conduct our experiments on 4 real-world datasets: Movielens, Netflix, Epinions and Yelp, and 3 kinds of different methods are chosen as a baseline. First is a traditional ranking model, SLI and SLIME, and the second is deep neural network recognition models, including NCF and NCR. And the final is a deep generative recognition models, including MonteVAE and AWAE. And we use recall and NCCG as metrics to evaluate the recognition performance. Okay, first we invest the performance, the effect of the parameters. We know that there are 3 parameters in our model. The first one is the dimensionality of Z, is the dimensionality of latent variable. The second one is the lambda A, is the regularization coefficient to measure the effect of the regularization term. And the third one is lambda B, is a coefficient to measure the effect of the ranking loss. So from here we know that a proposed model can have a good performance when we set the dimensionality at a small value, for example 115, and it can get a better performance. And also the lambda A can get a better performance at a small value. Okay. And finally, we compare the proposed methods to the baselines in terms of NDCG and recall. Also, we from 2 views to compare the proposed methods. The first view is all users, means that all users are included in the testing dataset to evaluate the performance. And the second one is the near co-star users, means that the users only have 5 or less than 5 feedback datasets will be used to the testing set. So from these 2 views, we can see that the proposed DGR have a better performance. And also we investigate the performance of the ranking model. Here the DGRR means that we remove the ranking response model and we only use the beta distribution, Beta-Bernoulli generative model to obtain a ranking score. And we can see that the DGR is outperformed better than the DGRR. So you can see that the ranking response model also play an important role in our model. So let's give a brief conclusion. And in this paper, we propose a deep generative ranking model for item recommendation that jointly model the generation of implicit feedback data and the creation of a pairwise ranking list. And we also give a generalization of our proposed model, and is theoretically guaranteed. And the experiments results show that the proposed methods has the ability to output a higher quality recommendation item list. So thank you. It's over.
Okay, so we do have an overflow room, and I wanted to ask if we have a question on this talk from that overflow room. Otherwise, we will take one from this room. Who has a good question? See somebody here in the front? Wait for the mic, because the overflow room wants to hear you even though they're not talking to us.
Okay, so just we'll put out the code on GitHub or something like that for evaluation. And second, so when you're comparing to these other methods, did you do the same kind of hyperparameter?
These methods.
Second,
What?
did you do the same hyperparameter optimization on the methods you're comparing against?
Okay. Here we use record and NDCT as a matrix, and we use three kind of different methods, SLAM and NCR and NCF as the deep recommendation methods, and also we compare methods with the deep generative model, multi-VAE.
So my question was, for your model, you obviously try to find the best hyperparameters. Hyperparameters found all the best settings for making your model great. You showed that. Did you also do that with the methods you're comparing to, or were they just taken as from the papers?
Yes, these results are obtained by our experiments because all of the data size is load is conducted by ourselves. So all of the results is obtained by ourselves. We run all the code and we turn all the hyperparameters by ourselves to get the best results here.
So for the other methods, you also did the hyperparameter optimization.
What?
For the method that was not your own method, did you also do hyperparameter optimization?
Yeah, we do a hyperparameter optimization.
That's great. All right, I would love to see the code. Thank you so much.
Okay, so let's thank the speaker again.